Tonight, you will look up and see thousands of stars. They will seem close. They will seem packed together like glitter scattered across a ceiling. Your eyes will tell you the universe is full, that the sky is crowded, that all those distant suns practically neighbour one another. Your eyes are lying. The nearest star beyond our sun is so far away that the fastest object humanity has ever launched, after nearly 50 years of non-stop flight, has crossed less than 1/1500th of the distance, and that is the closest one. The average gap between stars in our galaxy is a chasm so savage it breaks every intuition your brain has ever built about distance, travel, and belonging. The stars are not neighbours, they are castaways. If you enjoy having your assumptions about the universe completely dismantled, do me a favour and hit that like button and subscribe. It genuinely helps this channel keep making these deep dives into the cosmos. Now, get yourself comfortable. Let's begin. Go outside tonight. Find a place where the city lights cannot reach you. Drive if you have to. Find a hilltop, a field, a stretch of coastline where nothing electric competes with the sky. Let your eyes adjust for 20 minutes until your pupils open wide enough to drink in every photon the cosmos is willing to send. And then look up. What you see will take your breath away. Thousands of stars scattered across the darkness. Dense clusters near the galactic plane. Faint smudges where star clouds pile on top of each other until individual points blur together into rivers of light. The Milky Way itself cutting the sky in half like a luminous scar. Everywhere you look, stars, packed together, crowded, overlapping. Your brain processes this scene the same way it processes a city seen from an airplane window at night. Lights everywhere, density everywhere, fullness everywhere. Your brain is wrong. Not slightly wrong, not off by a small margin that a correction factor could fix. Your brain is catastrophically, fundamentally, almost comically wrong about what it is seeing when it looks at a night sky full of stars. Every intuition you form in that moment about proximity, about neighbourhood, about cosmic togetherness, is a lie manufactured by the physics of how your eyes work and the evolutionary constraints of a visual system that was never designed to interpret interstellar space. Here is the problem. Your eyes have no way to measure depth at astronomical distances. On Earth, your visual system is extraordinary. Binocular vision gives you depth perception out to a few dozen feet. Beyond that, your brain uses contextual cues. Objects that overlap appear closer. Objects that shrink with distance give you a sense of scale. Atmospheric haze tells you something far away is genuinely far away, because it looks blue and faded. These tricks work beautifully in the environment your ancestors evolved to navigate. A savanna, a forest, a coastline, distances measured in feet, yards, maybe miles. But point those same eyes at the night sky and every single depth cue vanishes simultaneously. There is no overlap because stars are points of light, not extended objects. There is no atmospheric gradient because the atmosphere above you is functionally transparent to starlight. There is no size diminishment because every star, regardless of whether it is 8 light-years away or 8,000, appears as the same dimensionless dot. Bright stars might seem closer, dim stars might seem farther, but brightness is not a reliable distance indicator. A dim star might be a faint red dwarf right next door. A brilliant star might be a supergiant thousands of light-years away masquerading as a neighbour. The result is devastating for your intuition. Your brain takes every star it can see, regardless of actual distance, and projects them all onto a single flat surface. A dome, a ceiling, a canvas where everything appears to exist at the same depth. Stars that are 4 light-years from Earth and stars that are 4,000 light-years from Earth get painted onto the same apparent plane. The sky becomes a photograph with no z-axis, a flat image with no indication that one point of light might be 1,000 times farther than the one right beside it. This is why the night sky looks crowded. Not because stars are physically packed together, But because your visual system has compressed a three-dimensional volume spanning thousands of light years of depth into a two-dimensional image, where everything appears equidistant, you are looking at stars scattered across an enormous cylinder of space stretching outward from Earth in every direction. But your brain renders that cylinder as a flat sheet. Every star in the column gets collapsed onto the same point. Depth vanishes, separation disappears, and the sky fills up. Strip away that illusion, and the reality is nothing like what your eyes report. Stars are not decorations on a shared ceiling. They are thermonuclear furnaces. Each one is a sphere of superheated plasma held together by its own gravity, powered by the fusion of hydrogen into helium in its core, at temperatures exceeding 15 million degrees. Our Sun is one such furnace. It measures 864,000 miles across. It converts 4 million tons of its own mass into pure energy every single second. It has been doing this for 4.5 billion years and will continue for roughly another 5 billion. That is what a single star is. A machine of almost incomprehensible violence and power burning in isolation. And the key word there is isolation. Because the distance between our Sun and its nearest neighbour is not something your brain can intuitively process. The nearest star to our solar system is Proxima Centauri. It is a small red dwarf, only about 12% of the Sun's mass, so dim that despite being the closest star to Earth beyond our own Sun, it is completely invisible to the naked eye. You would need a telescope just to see it. Proxima Centauri sits approximately 4.24 light-years from Earth. That number gets stated so frequently in astronomy that it has lost all emotional charge. 4.24 light-years. It sounds manageable. It sounds like a number that belongs in the same sentence as the word neighbour. It is not manageable. Let me show you what 4.24 light-years actually means. A light-year is the distance that light travels in 1 year. Light moves at 186,000 miles per second, not per hour, per second. In a single second, a beam of light crosses a distance roughly equivalent to circling the Earth 7.5 times. In 1 minute, light travels over 11 million miles. In 1 hour, it covers 670 million miles. In 1 day, it reaches 16 billion miles. Keep that pace going for an entire year, 365.25 days, and light covers approximately 5.88 trillion miles. Now multiply that by 4.24. The distance to Proxima Centauri is approximately 24.9 trillion miles. Written with digits, that number is so long it stops meaning anything. So let me try to make it mean something. If you could build a highway stretching from Earth to Proxima Centauri, and you drove a car at 60 miles per hour without ever stopping, no fuel breaks, no sleep, no death, just relentless driving at highway speed, the trip would take approximately 47 million years. You would need to drive for a span of time longer than the entire evolutionary history separating modern humans from the earliest known ancestors of the great apes. A span of time longer than the entire age of the Antarctic ice sheet would pass beneath your wheels, and you would still not be there. Or consider flight. A commercial jetliner travels at roughly 550 miles per hour. At that speed, reaching Proxima Centauri would take about 5.2 million years. Every civilization that has ever existed on Earth, from the first Sumerian cities to the phone in your pocket, occupies roughly 5,000 years. You would need 1,000 consecutive civilizations, each lasting as long as all of recorded human history, stacked end to end, just to complete one flight to the nearest star. But those comparisons use absurdly slow vehicles. What about something real? What about humanity's fastest spacecraft? Voyager 1 launched from Cape Canaveral on September 5, 1977. It flew past Jupiter in 79, past Saturn in 80, and then it kept going. It left the heliosphere in 2012 and entered interstellar space. As of early 2026, it is approximately 173 astronomical units from the Sun. It travels at roughly 38,000 miles per hour relative to the Sun. That is 17 kilometers per second. It is the fastest human-made object ever to leave the solar system. And right now, Voyager 1 is approaching a milestone that should terrify anyone who has ever casually described Proxima Centauri as nearby. In late 2026, Voyager 1 will reach a distance of 1 light day from Earth. 1 light day. That means a radio signal sent from Earth will take 24 hours to reach the spacecraft. The reply will take another 24 hours to come back. A simple hello and response will consume 2 full days. That milestone will arrive after nearly 50 years of continuous flight. Think about that. Voyager 1 has been flying through space for almost half a century. It has crossed the entire solar system and pushed beyond the boundary where the sun's influence ends. It has travelled farther from Earth than any object humanity has ever built. And after all of that, it has covered 1 light day. Proxima Centauri is 4 light years away. A light year contains 365.25 light days. 4.24 light years contains roughly 1,549 light days. Voyager 1, after 50 years, has crossed one of those 1,549 light days. Less than 1/1500th of the journey. Less than 7/100ths of 1%. If the trip to Proxima Centauri were a marathon, Voyager 1 has not yet finished the first 90 feet. It has been running for half a century, and it is still standing essentially at the starting line. At its current speed, Voyager 1 would need more than 70,000 years to reach Proxima Centauri. 70,000 years. For context, 70,000 years ago, anatomically modern humans had only recently begun migrating out of Africa. The entirety of civilization, agriculture, writing, mathematics, industrialization, spaceflight, all of it fits into a window. Roughly 1/7 of the time it would take our fastest probe to reach the nearest star. This is the first crack in the illusion. The nearest star is not merely far, it is far on a scale where human technology, at its absolute best, becomes functionally irrelevant. We do not have slow spacecraft. We have spacecraft that are miracles of engineering, objects moving at speeds no human body could survive, and those speeds are so laughably inadequate for interstellar distances that the gap between capability and requirement might as well be infinite. But the distance to Proxima Centauri is not just a problem of travel, it is a problem of communication. Light is the fastest thing in the universe. Nothing carries information quicker. If you could somehow build a laser powerful enough to transmit a message to a hypothetical receiver orbiting Proxima Centauri, that message would travel at the speed of light, the fastest speed permitted by physics, and it would still take 4 years and 3 months to arrive. A reply would take another 4 years and 3 months to come back. A single exchange of hello and hello back would consume 8.5 years. And here is an irony so sharp it should sting. The nearest star beyond the sun, the one celestial neighbour that is genuinely, physically closest to us, is invisible. You cannot see Proxima Centauri with your naked eyes, not from anywhere on Earth. Not under the darkest, clearest sky humanity has ever observed from. Not from the summit of Mauna Kea or the ice fields of Antarctica or the driest stretches of the Atacama Desert. Proxima Centauri shines at an apparent magnitude of roughly 11, which is roughly 100 times too dim for the human eye to detect without optical assistance. You need at least a modest telescope to see it at all, and even through that telescope it appears as nothing more than a faint reddish dot, utterly unremarkable, lost among thousands of brighter background stars. Think about what that means in the context of the sky you see at night. Every star visible to your naked eyes, every one of the roughly 5,000 points of light your unaided vision can detect from a perfectly dark site, is farther away than Proxima Centauri. Every single one. Sirius, the brightest star in the sky, is 8.6 light-years away, more than twice the distance to Proxima. Vega is 25 light-years away. Arcturus is 37. Betelgeuse is approximately 700. Deneb, one of the most luminous stars visible from Earth, sits roughly 2,500 light-years away. These are the stars that dominate your sky. that create the illusion of a packed and crowded cosmos. And they are all vastly farther than the one star that actually qualifies as nearest. The night sky is not showing you proximity, it is showing you luminosity. The stars you see are not the closest ones, they are the brightest ones, and brightness, at stellar scales, has almost nothing to do with distance. A star can be extraordinarily bright and extraordinarily far away. A star can be extraordinarily close and completely invisible. Your eyes sort the sky by luminosity, and your brain interprets that sorting as a distance map. But the map is wrong. The brightest stars are not the nearest. The nearest star is not bright. The sky is a luminosity catalogue masquerading as a neighbourhood guide. This is the deepest layer of the visual deception. It is not merely that your eyes flatten three-dimensional space into a two-dimensional dome. It is that the selection filter your eyes apply, brightness, is anti-correlated with proximity for most of the stars you can see. Proxima Centauri is a red dwarf, a class of star that comprises more than 70% of all stars in the Milky Way. Red dwarfs are small, cool, and extraordinarily dim. They burn hydrogen so slowly and so efficiently that they will outlive our Sun by trillions of years, but their luminosity is a tiny fraction of the Sun's. Proxima Centauri emits only about 0.0056% of the Sun's luminous output in visible light. Even at 4.24 light-years, that is not enough to register on your retina. This means the most common type of star in the entire galaxy is invisible to the human eye at even the shortest interstellar distances. The sky you see at night is a biased sample, skewed overwhelmingly toward rare, luminous giants and bright main-sequence stars that represent a small minority of the stellar population. The vast majority of actual stars, the red dwarfs that dominate every stellar census, are missing from your visual experience entirely. The sky appears crowded because the rare bright stars are visible across hundreds or thousands of light-years, stacking up along every line of sight. The common dim stars, the ones that are actually nearest and most numerous, contribute nothing to the spectacle. You are seeing the exceptions and missing the rule. And how do we know that Proxima Centauri is 4.24 light-years away? Not through theory, not through estimation, through one of the most elegant and direct measurement techniques in all of science, parallax. As the Earth orbits the Sun, it shifts position by roughly 300 million kilometers from one side of its orbit to the other. This shift causes nearby stars to appear to move very slightly against the background of far more distant stars, the same way a nearby lamppost appears to shift position against distant buildings when you move your head from side to side. The amount of apparent shift, measured in fractions of an arcsecond, directly reveals the star's distance through simple trigonometry. No assumptions, no models, pure geometry. The European Space Agency's Gaia spacecraft has measured the parallax of Proxima Centauri with extraordinary precision, pinning its distance at 4.2465 light-years, with uncertainties so small they are negligible for any practical purpose. This is not an estimate. It is not a rough figure. It is a measurement confirmed by direct geometric observation to an accuracy that leaves essentially no room for doubt. When I tell you the nearest star is 4.24 light-years away, that number carries the full weight of measured, verified, observational science. It is as reliable as the distance from New York to London, and it tells you that the closest star to the Sun, the best case, the absolute minimum gap between our world and another sun, is approximately 25 trillion miles of void that your fastest spacecraft would need over 70,000 years to cross. Imagine conducting a conversation on those terms. You send a question on your 30th birthday. The answer arrives when you are 38. You respond, and the next reply reaches you when you are 47. 2 exchanges of basic dialogue have consumed 17 years of your life. And this is communication with the closest star. Stars even slightly farther away turn conversation into something that spans generations. A message sent to a star 15 light-years away would not receive a reply for 30 years. A message to a star 50 light-years away means a century-long wait. The speed of light, the absolute fastest information can travel, transforms even modest stellar distances into communication barriers measured in human lifetimes. This changes the meaning of what it means to be a neighbour in space. On Earth, a neighbour is someone you can speak to, someone you can reach, someone whose existence is confirmed not just by observation, but by interaction. You can see them, talk to them, visit them. Proximity implies relationship, but at stellar distances, proximity implies almost nothing. Proxima Centauri is right there in astronomical terms, the closest star to our Sun, and yet it is so remote that no human technology can reach it, no message can be exchanged in a human lifetime without decades of silence between words, and no physical object we have ever built has covered more than a tiny fraction of 1% of the distance. If that is what the nearest star looks like, what does the rest of the galaxy look like? To understand why that question matters, you first need to feel the distance to Proxima Centauri, not as a number on a page, but as a physical weight pressing against every assumption you hold about the night sky. When you look up and see those thousands of stars appearing to cluster together in a dense canopy, you need to understand that each of those points of light is separated from its nearest companion by chasms that make the Earth to Proxima gap look routine. The Alpha Centauri system, of which Proxima is one member, gives us one more critical piece of this picture. Proxima Centauri is actually part of a triple star system. The other two members are Alpha Centauri A and Alpha Centauri B, a binary pair of Sun-like stars that orbit each other every 80 years. Proxima orbits this pair at a distance of about 0.21 light-years. That is roughly 13,000 astronomical units. An astronomical unit is the distance between Earth and the Sun, about 93 million miles. So Proxima Centauri is 13,000 times the Earth-Sun distance from its own binary companions. Even within a single star system, the separations are enormous. Proxima Centauri is gravitationally bound to Alpha Centauri A and B, meaning they are a family, a linked system moving through space together. And yet the distance between the members of that family is so large that light needs 2.5 months to travel from the binary pair to Proxima, a star system where the members are separated by trillions of miles. Now consider that this entire triple system is the nearest stellar group to our Sun. Beyond it, the distances only grow. Barnard's star, the next closest individual star, lies 5.96 light-years away. Wolf, 359, sits 7.86 light-years out. Lalande, 21185, is 8.3 light-years distant. Sirius, the brightest star in our sky, is 8.6 light-years away. These are the Sun's closest neighbours in every direction, and the gaps between them are measured in light-years, each light-year representing nearly 6 trillion miles of empty, featureless, silent vacuum. You could fit an almost obscene number of solar systems into these gaps. Our entire solar system, measured from the Sun out to the edge of the Oort cloud, the vast shell of icy objects surrounding the outermost reaches of our Sun's gravitational influence, spans roughly 2 light-years in diameter. That means you could fit 2 entire solar systems end to end in the gap between our Sun and Proxima Centauri and still have room left over. The space between stars is not a thin margin. It is an abyss that dwarfs the systems it separates. And here is where the first true shock should begin settling into your bones. All of this, every horrifying distance I have described so far, concerns exclusively the nearest stars, the closest ones, the galactic neighbours, the stars that astronomy calls nearby. Proxima Centauri at 4.24 light-years, Barnard's star at 5.96, Sirius at 8.6. These are the easy cases, the short trips, the stars you would aim for first if you ever somehow develop the technology to leave the solar system. The vast majority of stars in our galaxy are not 4 light-years away, they are not 8 light-years away. They are hundreds of light-years away. Thousands, tens of thousands. The Milky Way stretches roughly 100,000 light-years from edge to edge, with some measurements suggesting it may be closer to 200,000, when you include the outer halo. The Sun sits about 26,000 light-years from the galactic center. Stars on the far side of the galaxy are so distant that the light you would see from them tonight left their surfaces when our ancestors were still learning to build shelters from mammoth bones. But the sheer width of the galaxy is not the real story. Width is just a number. The real story is what happens when you start asking how those hundreds of billions of stars are distributed across that enormous volume. How tightly are they packed? How much empty space lies between them? And when you start answering those questions, the night sky stops looking full and starts looking like something far more unsettling. The distance to the nearest star already feels almost unbearable. The idea that most stars are separated by gaps equal to or greater than that distance, repeated hundreds of billions of times across a galaxy-sized volume, is where the true horror of interstellar space begins to reveal itself. And that is exactly where we are going next. Everything you learned in Part 1 concerned one star. One single, specific distance, 4.24 light-years to Proxima Centauri. And that distance, as we saw, was already enough to break every intuition your brain has about what it means for something to be nearby. But Proxima Centauri is an outlier. Not because it is unusually far, but because it is unusually close. It is the best-case scenario, the shortest possible trip, the absolute minimum distance between our Sun and another star. Everything else in the galaxy is the same distance or worse. Now it is time to stop thinking about one star and start thinking about all of them. The Milky Way contains somewhere between 200 billion and 400 billion stars. That number gets repeated so often in popular astronomy that it has become a kind of background statistic, impressive but abstract. People hear it and think fullness. They think abundance. They imagine a galaxy teeming with stars the way a city teems with people. Hundreds of billions of anything sounds like a lot, and it is a lot, until you understand the volume those stars have to fill. Our galaxy is not a small container. The disk of the Milky Way spans roughly 100,000 light-years in diameter, possibly up to 200,000 depending on how you define the outer boundary. The disk is approximately 1,000 to 2,000 light-years thick in the region near the Sun. When you calculate the total volume of this structure, even using conservative estimates, you arrive at a number in the trillions of cubic light-years. Some calculations place the volume of the galactic disk alone at roughly 8 trillion cubic light-years, and that does not include the vast, diffuse stellar halo that extends tens of thousands of light-years above and below the plane. Take 400 billion stars, place them inside 8 trillion cubic light-years of space, divide. The result is a stellar density of approximately 0.05 stars per cubic light-year. In the neighbourhood of the Sun, careful surveys that account for dim red dwarfs and other hard-to-see objects place the local density at roughly 0.004 stars per cubic light-year. That means for every cubic light-year of space around us, a volume measuring 6 trillion miles on each side, there is on average less than 1/200th of a star. You would need to search through 250 cubes of that size before you statistically expected to find a single stellar object. Translated into distances, this means the average gap between neighbouring stars in the Sun's region of the galaxy is approximately 5 light-years. About 30 trillion miles of nothing between one star and the next. And this is in a relatively populated arm of the galaxy. This is not the sparse outer halo or the empty gaps between spiral arms. This is the galactic suburbs, the kind of region where stars are reasonably common by Milky Way standards. 5 light-years, 30 trillion miles. That is the typical gap between neighbours. But that number is still just a number. Let me make you feel it. Imagine shrinking the Sun down to the size of a grapefruit. A round, bright sphere sitting on a table in front of you. At this scale, the Earth would be a tiny grain of sand, orbiting about 40 feet away. Jupiter would be a small marble, roughly 210 feet from the grapefruit. Neptune, the outermost major planet, would be a slightly smaller marble, almost a quarter of a mile from the Sun. The entire solar system, from the Sun out to Neptune's orbit, fits within a circle roughly half a mile wide. Now, where is the nearest star? At this scale, with the Sun as a grapefruit on your table, Proxima Centauri would be another small object, a cherry, sitting in a city approximately 2,200 miles away. If you placed your grapefruit sun on a table in Los Angeles, the nearest star would be sitting on a windowsill somewhere in Virginia. Between those two tiny fruits stretches the entire width of North America, across deserts and mountain ranges and prairies, with nothing in between but empty tabletop, no stars in between, no objects, no rest stops, no gas stations, just 2,200 miles of absolutely nothing, with a grapefruit on one end and a cherry on the other. That is the scale model of the nearest star. And remember, that is the closest one, the best case. At this same grapefruit scale, the average distance to a typical neighbouring star would be closer to 3,000 miles. Barnard's star would be roughly 3,100 miles away. Sirius would be about 4,500 miles from your tabletop sun. Sit with that image for a moment. A grapefruit in Los Angeles and a cherry in Madrid. That is what the night sky is actually showing you when it displays two stars that appear to sit right next to each other. And now multiply that emptiness by hundreds of billions of repetitions across the galaxy. That is the Milky Way, not a dense cloud of stellar objects pressed together in radiant abundance. A scattering of grapefruits and cherries and marbles separated by thousands of miles of void, repeating over and over until the pattern spans a disk 100,000 light-years wide. This emptiness is not figurative. The space between stars is genuinely, physically, almost perfectly empty. Interstellar space is the closest thing nature has to a perfect vacuum, and it is a vacuum that would make any laboratory on Earth weep with envy. The best vacuum chambers humans have ever built, using the most advanced pumps and the most carefully sealed enclosures, can remove gas molecules until only a few hundred remain per cubic centimetre. Interstellar space, in an average region between stars, contains roughly 0.1 to 1 atom per cubic centimetre. Not molecules, atoms, mostly hydrogen, the simplest element, drifting alone through a void so sparse that the distance between individual atoms can be measured in centimetres. This means that interstellar space is roughly 100 to 1,000 times emptier than the best vacuum humanity has ever created in a laboratory. If you were somehow placed into the void between two stars, you would experience nothing. No air, no pressure, no warmth, except for the faint cosmic microwave background radiation hovering at 2.7 degrees above absolute zero. No light beyond the distant pinpoints of stars that would look almost exactly like they look from Earth, because you would still be so far from all of them that none would appear as more than a dot. You would float in a darkness so thorough and a silence so complete that even the concept of location would begin to lose meaning. There are no landmarks in interstellar space, no features, no terrain, just hydrogen atoms spaced centimetres apart in a silence so absolute and a blackness so total that the distance between any two landmarks is measured not in miles, but in light years. Scattered through this void at extremely low densities are cosmic rays, high-energy particles accelerated by supernovae and other violent events, moving at close to the speed of light. There are faint magnetic fields threading through the interstellar medium, weak enough that they would be undetectable by any human sense. There are occasional wisps of interstellar dust, microscopic grains of carbon, silicon and ice, that collectively make up less than 1% of the interstellar medium's already negligible mass. And there is nothing else. No structure, no geography, no substance worth naming. This is what lies between every pair of stars in the galaxy. 30 trillion miles of this, repeated over and over and over, hundreds of billions of times, forming a web of emptiness so dominant that the stars themselves become the exception rather than the rule. When you look at the night sky, you are seeing the exceptions, the rare, isolated points where matter clumped together densely enough to ignite nuclear fusion. Everything between those points is void, and the void dwarfs everything it surrounds. Now let us talk about what those distances mean for anything trying to cross them. Earlier, I showed what happens when you point Voyager 1 at Proxima Centauri. 70,000 years of flight for the nearest star. But Voyager is not the only way to think about interstellar speed. Let us survey the full range of propulsion technologies humanity has built or seriously proposed, and watch each one crash against the wall of interstellar distance. Chemical rockets are what launched every human mission in history. The Saturn V that carried astronauts to the moon, the Atlas and Delta rockets that launched satellites, the Falcon 9 that resupplied the International Space Station. These rockets work by burning chemical propellant and expelling hot gas at high speed. They are powerful, proven, and utterly hopeless for interstellar travel. The fastest chemical rocket escape velocities achieved are in the range of 10 to 12 kilometers per second. At 12 kilometers per second, reaching Proxima Centauri would take over 106,000 years. You would need a flight duration longer than the span separating modern humans from the very first appearance of behavioral modernity in the archaeological record. But before we climb the ladder of propulsion technologies, we need to confront something the speed numbers alone cannot convey. It is not enough to know how long each engine takes to reach Proxima Centauri. You need to understand what those journeys actually cost in energy and what they actually do to a spacecraft trying to survive the crossing. Because the distance between stars does not merely impose a time penalty. It imposes a physics penalty so severe that the act of crossing interstellar space becomes a war against the fundamental equations of motion and thermodynamics. A war that every propulsion system we have ever built is losing by orders of magnitude. Start with energy. The most basic equation in rocket science is the Tsiolkovsky rocket equation, which describes the relationship between a spacecraft's final velocity, the velocity of its exhaust, and how much fuel it must carry. The equation is exponential. That word should alarm you. It means that every incremental increase in speed demands not a proportional increase in fuel, but a multiplicative one. To go twice as fast, you do not need twice as much fuel. You need the fuel mass squared. To go 3 times as fast, you need it cubed. The numbers escalate so rapidly that they become physically absurd at interstellar velocities. Consider a modest goal: accelerating a spacecraft the mass of Voyager 1, roughly 720 kilograms, to just 1% of the speed of light, using a conventional chemical rocket. 1% of light speed is 3,000 kilometers per second. The exhaust velocity of the best chemical rockets is about 4.5 kilometers per second. Plug those numbers into the Tsiolkovsky equation, and the required fuel mass exceeds the mass of the observable universe. Not the mass of the Earth, not the mass of the Sun, not the mass of the galaxy, the mass of the observable universe. Every atom in every star, in every galaxy, in every direction, converted entirely to rocket fuel, would not be enough to push Voyager 1 to 1% of light speed using chemical propulsion. That is not an exaggeration for dramatic effect. That is the mathematics. The exponential nature of the rocket equation annihilates chemical propulsion at interstellar velocities so completely that the concept is not merely impractical but physically impossible. Chemical rockets are miracles of engineering for reaching orbit, for traveling to the moon, for sending probes across the solar system. For interstellar distances, they are not inadequate. They are irrelevant. Higher exhaust velocities improve the equation, but they do not escape it. Every rocket-based propulsion system, whether it expels ionized gas, superheated hydrogen from a nuclear reactor, or the plasma from nuclear detonations, faces the same exponential wall. The specific numbers change, the conclusion does not. Reaching even a few % of light speed with any system that must carry its own reaction, mass demands fuel quantities that escalate from impractical to physically absurd as target velocity climbs. The exponential function is merciless. It does not care how clever the engineering is. It simply demands more mass than the universe can provide at velocities that interstellar distances require. Systems that bypass the rocket equation entirely offer the only theoretical escape: A sail pushed by an external energy source carries no fuel at all, sidestepping the exponential barrier. But even this approach demands staggering energy input. To push a payload of just a few grams to 20% of light speed, current proposals require a ground-based laser array delivering 100 gigawatts of continuous power for approximately 10 minutes per launch. 100 gigawatts is roughly the total electrical generating capacity of a medium-sized industrial nation. The entire United States generates approximately 1,100 gigawatts at peak capacity. Pushing a few grams to the nearest star would consume nearly 10% of American electrical output focused into a single coherent beam, aimed at a target the size of a bedsheet, accelerating at thousands of kilometers per second, scaling up to a payload of meaningful mass, something carrying instruments capable of returning detailed data or, far more ambitiously, biological passengers, would require energy budgets exceeding the output of entire civilizations. The energy cost of interstellar travel is not an engineering problem waiting for a clever solution. It is a physics problem arising from the fundamental relationship between mass, velocity, and energy. Kinetic energy scales with the square of velocity. Doubling your speed quadruples your energy requirement. Reaching 10% of light speed requires 100 times the energy of reaching 1%. Reaching 50% requires 2,500 times. And all of this energy must be generated, stored, directed, and applied without destroying the spacecraft in the process. The distances between stars do not merely demand time, they demand energy on a scale that challenges the productive capacity of entire worlds. But even if you solve the energy problem, even if some future civilization builds laser arrays or fusion drives or antimatter engines capable of pushing meaningful payloads to significant fractions of light speed, the void between stars presents a second set of challenges that are equally brutal. The interstellar medium is almost empty. Almost. But at velocities approaching even a few percent of light speed, almost empty becomes functionally lethal. Interstellar space contains roughly 1 hydrogen atom per cubic centimeter on average, with regional variations ranging from 0.1 atoms in the hottest, most diffuse regions to several thousand atoms in dense molecular clouds. At everyday speeds, these atoms are irrelevant. At 1% of the speed of light, 3,000 kilometers per second, each hydrogen atom strikes the spacecraft with the energy of a small bullet. At 10% of light speed, each atom impacts with energies comparable to those produced in particle accelerators. At 20%, the energy per atom reaches levels associated with cosmic ray impacts capable of disrupting electronics, damaging biological tissue, and sputtering material from any surface they strike. A spacecraft traveling at 10% of light speed through a medium containing 1 hydrogen atom per cubic centimeter would encounter approximately 3 billion atoms per square centimeter of forward-facing surface every second. Each impact deposits energy into the hull. The cumulative effect is equivalent to being bombarded by a continuous stream of high-energy radiation. Over a journey lasting decades, this bombardment can erode shielding, degrade structural materials, damage sensitive instruments, and deliver radiation doses lethal to any biological organism aboard. The interstellar medium is not just empty space to be crossed. It is a gauntlet of high-velocity particle impacts that intensifies with every increase in speed. Interstellar dust makes the problem dramatically worse. Dust grains in the interstellar medium are microscopic, typically measuring fractions of a micrometer, composed of silicates, carbon compounds, and ice. At rest, they are harmless. At 10% of light speed, even a grain 1 micrometer across, weighing roughly a trillionth of a gram, strikes with enough kinetic energy to vaporize itself and a small crater of hull material on impact. At 20% of light speed, the energy quadruples. Larger grains, 10 micrometers across, impact with the energy of a small caliber bullet. A spacecraft's forward-facing surfaces would accumulate thousands of such impacts over a journey spanning light years, each one ablating material, degrading shielding, and creating microfractures in structural components. Over a journey spanning 4 or 5 light years, the spacecraft would encounter billions of such grains. The cumulative damage from dust alone could be catastrophic without shielding massive enough to significantly increase the spacecraft's total mass, which circles back to the energy problem and makes it worse. The thermal environment compounds everything. A spacecraft in interstellar space, far from any star, radiates heat into a background at 2.7 Kelvin, barely above absolute zero. Any onboard systems generating heat, computers, life support, instruments, must reject that heat into this near-zero sink, which requires radiators of sufficient size and efficiency. Meanwhile, the particle bombardment at high velocity deposits heat into the forward-facing surfaces. At 10% of light speed, the energy flux from impacting hydrogen atoms and dust can raise the temperature of forward shielding significantly, creating a thermal management problem that grows worse at higher speeds. The spacecraft must simultaneously manage extreme cold on its shadowed surfaces and increasing heat on its forward face, a thermal gradient that stresses materials and complicates structural design. Then, there is time. A journey to Proxima Centauri at 5% of light speed takes approximately 85 years. At 10%, roughly 43 years. At 20%, about 21 years. These durations demand that every system aboard the spacecraft, propulsion, navigation, communication, power, structural integrity, data storage, and potentially life support, must function continuously without major failure for decades. No human machine has ever operated in the space environment for 85 years. Voyager 1 has survived 49 years through a combination of extraordinary engineering and conservative power management, but it is moving at a tiny fraction of 1% of light speed and has experienced none of the high-velocity bombardment that an interstellar crossing would impose, extending mission lifetimes to decades while simultaneously withstanding particle erosion, radiation damage, thermal stress, and the cumulative degradation of every mechanical and electronic component aboard is an engineering challenge without precedent. These are not abstract concerns. They are physical realities imposed by the interstellar medium and the velocities required to cross it in timescales shorter than civilizational lifetimes. The void between stars is not just far, it is hostile. Not hostile in the way a desert is hostile, with heat and thirst and predators. Hostile in the way that hard vacuum combined with high-velocity particle bombardment, combined with extreme thermal gradients, combined with multi-decadal mission durations is hostile. The emptiness between stars is not passive. At the speeds necessary to cross it, it actively fights you. And all of this applies to the nearest star, the shortest crossing, the best-case scenario. For stars 10, 20, or 50 light-years away, every problem intensifies proportionally. More time in transit means more cumulative particle damage. More distance means more energy required. More exposure to cosmic rays, dust, thermal cycling, and the slow degradation of every material and system aboard. The void between stars is not merely wide, it is punishing, in exact proportion to its width. Ion drives are the next step up. Instead of burning chemicals, ion drives accelerate electrically charged atoms using electromagnetic fields. They produce far less thrust than chemical rockets, but they can run continuously for months or years, gradually building speed. The Dawn spacecraft used ion propulsion to explore the asteroid belt, reaching speeds of roughly 11 kilometers per second relative to the Sun. But even advanced ion drives, pushed to their theoretical limits, top out at speeds that reduce the Proxima Centauri trip to perhaps 30 to 40,000 years. Better than chemical rockets, still longer than all of recorded human civilization. Nuclear thermal propulsion replaces chemical combustion with a nuclear reactor, heating propellant to extreme temperatures and expelling it at higher velocities than chemical rockets can achieve. NASA's Project Nerva tested nuclear thermal engines in the 1960s and 70s. These systems could potentially reach exhaust velocities 2 to 3 times higher than chemical rockets. Even with those improvements, crossing 4.24 light-years would require tens of thousands of years. Nuclear thermal propulsion is transformative for traveling within the solar system, reaching Mars in weeks rather than months. For interstellar distances, it barely changes the equation. Nuclear pulse propulsion is the most dramatic concept ever seriously studied. Project Orion, proposed in the 1950s and 60s, envisioned detonating nuclear bombs behind a spacecraft and riding the shockwaves. The design was theoretically capable of reaching 3 to 5% of the speed of light if pushed to its extreme configurations. At 5% of light speed, Proxima Centauri would be approximately 85 years away. For the first time, the trip compresses into something resembling a human timescale, though it would still span an entire lifetime. But Project Orion was never built. Its reliance on nuclear detonations made it politically impossible, and the Partial Test Ban Treaty of 1963 effectively killed it. The concept remains on paper, tantalizing and unreachable. And then there was Breakthrough Starshot. Announced in 2016 by physicist and investor Yuri Milner alongside Stephen Hawking, the project proposed something radically different. Instead of carrying fuel, spacecraft would be propelled by an enormous ground-based laser array, pushing against ultralight reflective sails. Tiny probes, each weighing only a few grams, would be accelerated to 20% of the speed of light. At that velocity, Proxima Centauri becomes a 20-year journey. For the first time, a round-trip communication with the nearest star compresses into a single human career. Launch the probe at age 30. Receive data at age 55, accounting for the flight plus the 4-year signal return. It was the most ambitious interstellar travel concept ever funded. $100 million committed to a proof of concept. And as of September 2025, the project is on indefinite hold. Roughly $4.5 million were spent across about 30 research contracts over 9 years. Laboratory experiments at Caltech in early 2025 achieved the first direct measurements of radiation pressure on ultra-thin sail membranes, confirming the basic physics. But the engineering challenges remain immense. The laser array would require the power output we already described, focused with a precision no existing system can deliver. The sail materials must survive being heated to extreme temperatures during acceleration. The probes must function after being subjected to forces exceeding 10,000 times Earth's gravity during the 10-minute acceleration phase. And even if all of those problems are solved, the data the probes return would be limited. A gram-scale spacecraft passing through the Alpha Centauri system at 20% of the speed of light would have only seconds to observe anything before hurtling past at 60,000 kilometers per second. 20% of light speed is the fastest serious interstellar proposal ever funded, and it was not enough to make the nearest star feel close. It compressed the journey from millennia to decades, which is a staggering achievement conceptually, but even 20 years of flight represents a commitment so extreme that humanity has never sustained a single engineering project for that duration. And that is for a flyby, not a stop, not a landing, not a colony, a flyby of the nearest star, during which your spacecraft screams past at 1/5 the speed of light and you get a few seconds of close-range data before it disappears into the dark forever. This is the wall that interstellar distance builds. It does not merely make travel difficult, it makes travel almost definitionally incompatible with human timescales and human engineering. Every propulsion technology humanity has built or imagined, from chemical rockets to nuclear pulse drives to laser sails, either fails to reach the nearest star in less than thousands of years or requires engineering so far beyond current capability that even well-funded projects stall before leaving the laboratory. The distance is not a challenge to be overcome with better rockets. It is a structural feature of reality that reshapes what travel, communication, and human reach can possibly mean. And here is the part that should truly unsettle you. Everything I've described in this section has still been focused on the nearest stars. The friendly neighborhood, the short trips, 5 light years between neighbors, 4.24 to Proxima, 6 to Barnard Star, 8 to Sirius. These are the grocery store distances of interstellar space. Walk outside and drive a few minutes. Cosmically trivial, But the average 5 light-year gap between stars near the Sun is not representative of the galaxy as a whole. It is a local condition, specific to our position in a relatively populated region of the Orion Arm. Move to a different part of the galaxy, and the numbers change, almost always for the worse. Between the spiral arms of the Milky Way lie vast interarm regions where stellar density drops significantly. Stars in these zones may be separated by 10, 15, or 20 light-years on average. A star born in one of those regions would look out at a sky noticeably sparser than ours, with fewer visible neighbours and larger stretches of uninterrupted black between them. The trip to the nearest star from such a location would not be 4 light-years. It might be 15. At Voyager speeds, that is not 70,000 years, but over 260,000 years. At 20% of light speed, not 20 years but 75, above and below the galactic disk, the situation becomes even more extreme. The stellar halo of the Milky Way extends tens of thousands of light-years in every direction perpendicular to the disk. Halo stars are ancient objects, many of them among the oldest in the galaxy, orbiting in elongated paths far from the crowded plane. In the halo, stellar density plummets. Stars may be separated by dozens or even hundreds of light-years. An observer on a planet orbiting a halo star would see a sky of extraordinary emptiness. The Milky Way's disk would appear as a faint band of light in the distance, and the nearest star might be so far away that reaching it, even at significant fractions of the speed of light, would require centuries. And then there are the true outskirts. Astronomers have identified stars belonging to the Milky Way at distances exceeding 700,000 light-years from the galactic center, far out in the most tenuous reaches of the stellar halo. These stars exist in almost complete isolation. Their nearest neighbors might be thousands of light-years away. They orbit the galaxy on paths so elongated that a single orbit takes billions of years. From the perspective of one of these distant stars, the galaxy would be a faint smudge in the sky, its hundreds of billions of stars compressed into a soft glow too distant to resolve. The concept of a neighbouring star would be essentially meaningless. The distance to the nearest companion would exceed what even light could cross in a human civilization's entire lifespan. This variation in stellar density reveals something crucial about the Milky Way that the night sky hides from us. We live in a relatively friendly part of the galaxy. Our stellar neighbourhood, with its 5 light-year average spacing and its handful of nearby stars within 10 light-years, is cosmically privileged. Not special, not centred, not uniquely important, but denser than much of the galaxy. We happen to sit in a region where the nearest star is only 4 light-years away, and we still cannot reach it. Other regions of the galaxy are far lonelier, and for any hypothetical observers in those regions, the isolation we already find staggering would be multiplied many times over. The 5 light-year gap that characterises our neighbourhood is not the galaxy's heartbeat. It is a local courtesy. A fortunate density that gives us the illusion of proximity when we look up at the night sky and see a few thousand visible stars packed into an apparently crowded field. Strip away the optical illusion, zoom out past the comfortable neighbourhood, and the galaxy begins to reveal its true character. It is not a structure defined by its stars. It is a structure defined by the emptiness between them. The stars are incidents, brief interruptions in a void so extensive and so dominant that the space between any 2 stars contains more nothing than most human minds can hold. And when you realise that even our cosy local neighbourhood, with its relatively tight 5 light-year spacing, already defeats every propulsion technology humanity has ever built or seriously imagined, the full scale of galactic emptiness stops being an abstraction and starts becoming something you can feel pressing against your chest. What that emptiness looks like when you pull back and see the entire galaxy at once is what we are about to confront. There is a photograph you have probably seen. It appears in every astronomy textbook, on every science website, in every documentary about the cosmos. It shows the Milky Way from the outside, a grand spiral viewed from a vantage point millions of light-years above the galactic plane. sweeping arms dense with blue-white stars, a bright central bulge glowing gold and amber, lanes of dark dust threading between the spiral structures. The whole thing looks solid, packed, heavy with stars. It radiates density the way a crowded stadium radiates noise. You look at that image and your brain says full. Your brain says rich. Your brain says overflowing with matter and light. That image is not a photograph. It cannot be. We live inside the Milky Way. No spacecraft has ever left the galaxy. No camera has ever captured it from the outside. Every external view of the Milky Way you have ever seen is an artist's rendering based on observations of other spiral galaxies and our best models of our own galaxy's structure. The image is educated imagination. It is very good educated imagination, built on decades of radio surveys and infrared mapping and stellar catalogues. But it is not what the Milky Way looks like. It is what the Milky Way would look like if you compressed all of its depth into a flat painting and then set the brightness far higher than reality. The real Milky Way, experienced from inside, is nothing like that image. And the gap between the painting and the reality is where the deepest shock about stellar distance lies. Let me dismantle the painting. 400 billion stars sounds like an incomprehensible multitude. But the galaxy is not a room, it is a volume. And volume punishes large numbers far more viciously than intuition expects. The disk of the Milky Way spans roughly 100,000 light-years in diameter and about 1,000 light-years thick in the region near the Sun. As we saw earlier, the volume of this structure runs to roughly 8 trillion cubic light-years, and that does not include the vast, diffuse stellar halo extending tens of thousands of light-years above and below the plane. Take 400 billion stars, place them inside 8 trillion cubic light-years of space. Divide. The result is that each star commands an average private territory of roughly 20 cubic light-years. 20 cubic light-years per star. Each star, on average, owns a volume of space measuring approximately 2.7 light-years on each side, a cube of emptiness so vast that light itself needs nearly 3 years to cross it. And that cube contains, on average, one star. One. Surrounded by 16 trillion miles of void in every direction before the next star's territory begins. If you picked a random point inside the Milky Way's disk, a truly random coordinate with no bias toward known stars or familiar constellations, the overwhelming probability is that you would find yourself in empty space. Not near a star, not within a solar system, not anywhere close to anything at all. You would be floating in interstellar void with the nearest star multiple light years away, in some direction you would have no way to determine without instruments. The chance of randomly landing within even 1 light year of any star is small. The chance of landing within the boundaries of a solar system, within the gravitational sphere of influence of a star and its planets, is vanishingly tiny. Run the numbers more precisely. Our solar system's physical extent, measured from the Sun to the outermost fringes of the Oort cloud, stretches roughly 1 light year in every direction, giving the Sun a sphere spanning a volume of approximately 4 cubic light-years. In a galaxy of 8 trillion cubic light-years, that means our solar system occupies less than 1/1000th of 1% of the galaxy's volume. If the Milky Way were a large lake, our entire solar system would be a single grain of sand resting somewhere on its bed, occupying so little of the total volume that finding it by random search would take longer than a human lifetime. This is the first thing the photograph gets wrong. The Milky Way is not full of stars the way a bowl is full of fruit. It is full of stars the way the Pacific Ocean is full of ships. There are many ships on the Pacific, thousands at any given time. But if you dropped blindfolded onto a random point on the Pacific's surface, you would see nothing but water stretching to every horizon. The ships exist. They are real. They are numerous. But the ocean is so overwhelmingly larger than all of them combined that they vanish into it. Each ship is an isolated object surrounded by an enormity of blue nothing. That is the galaxy. Stars are the ships. The void is the ocean. And the ocean is winning by a margin so extreme that calling the galaxy a collection of stars is almost misleading. It would be more accurate to call it a collection of empty space that happens to contain stars. Now consider what this means for the galaxy's visual appearance from inside. When you look at the night sky and see the Milky Way as a bright band of light, you are not seeing a dense wall of stars. You are seeing the accumulated glow of millions of stars arrayed along the line of sight through the galactic disk. Your eye collects photons from stars at every distance along that line of sight. 4 light years away, 40, 400, 4,000. All of those photons pile onto the same patch of your retina. The combined effect looks bright, dense, packed. But each of those stars is separated from its neighbours by light years of void. You are seeing through the galaxy, stacking layers of isolated stars on top of each other until the accumulation creates an illusion of density. It is like looking through a forest from the edge. A single line of trees, evenly spaced 10 meters apart, looks sparse when you stand perpendicular to it. You can see the gaps between each trunk. Walk to the end of the line and look down its length, and the trees overlap visually. The forest looks dense and impenetrable, no gaps visible. But the physical spacing between the trees has not changed. Only your viewing angle has. The galactic plane works the same way. Looking perpendicular to the disk, you see relatively few stars, and the sky appears dark. Looking along the disk, you stack thousands of light years of depth into a single visual corridor, and the sky brightens into the familiar Milky Way band. The density is an artifact of perspective. The emptiness is real. This distinction matters enormously because it controls how people think about the galaxy. Every image of the Milky Way that makes it look solid reinforces a mental model where stars are packed together, where the galaxy is a place of cosmic closeness, where hundreds of billions of suns create a rich environment teeming with potential for connection, contact, travel. But the physical galaxy is almost nothing like that mental model. The physical galaxy is a place where the dominant experience, from almost any position within it, is isolation, emptiness, separation from the nearest star by distances that reduce even light to a slow crawl. Let me push the numbers further. I said the average star commands 44 cubic light years of private space, but averages conceal enormous variation, and the variation almost always makes the emptiness worse. The galactic disk is not uniformly populated. Stars concentrate in the spiral arms, where gas clouds compress and trigger star formation. Between the arms, stellar density drops. Some interarm regions contain less than half the stellar density of the arms themselves, meaning individual stars may be separated by 7, 8, or 10 light years on average. A star born in one of these interarm voids lives in a neighborhood so sparse that its closest companion might be 50 or 60 trillion miles away. Above and below the disk, the situation deteriorates rapidly. The thin disk, where most stars reside, has a vertical extent of only about 1,000 light years. Beyond that lies the thick disk, older and sparser, stretching to perhaps 3,000 light years above and below the midplane. Beyond the thick disk is the stellar halo, a vast spherical region extending tens of thousands of light years outward. In the halo, stellar density drops to a fraction of a percent of the disk's density. Halo stars are ancient, metal-poor objects orbiting on wild elliptical trajectories, and they are profoundly alone. The nearest neighbour to a typical halo star might be dozens of light years away. Some halo stars exist in regions so sparse that the nearest companion lies over 100 light years distant. The galaxy also thins out dramatically toward its outer edges. Beyond a radius of roughly 40 or 50,000 light years from the centre, the disk begins to fade. Star formation drops off. The population becomes dominated by older, dimmer stars with wider average separations. At the very outermost reaches, astronomers have found individual stars orbiting at distances of hundreds of thousands of light years from the galactic centre. These stellar wanderers exist in near total isolation. They belong to the Milky Way gravitationally, but they inhabit a region where the concept of stellar neighborhood has effectively ceased to exist. Contrast this with the galactic center, where conditions are radically different. Within a few parsecs of the supermassive black hole Sagittarius A star, stellar densities soar to roughly 10 million stars per cubic parsec. At those densities, the average distance between neighboring stars shrinks to about 1,000 astronomical units, roughly a light week. A sky viewed from the core would be blazing with stellar light in every direction, thousands of stars visible brighter than Sirius, the combined glow potentially bright enough to eliminate true darkness entirely. The galactic center represents the one region where stars genuinely are packed close together. To feel what these density variations actually mean, step out of your own sky for a moment and imagine standing on a planet in three very different parts of the Milky Way. First, place yourself on a world orbiting a star in one of the interarm regions, the sparse stretches of galactic disk between the major spiral arms. So your star sits in a zone where stellar density is dropped to a tenth or less of the density near the Sun. You walk outside at night and look up. The sky is dark, genuinely dark. You can still see stars, but far fewer of them. The Milky Way band, the edge-on glow of the galactic disk, is still visible, but it appears thinner and less luminous than it does from Earth. Your nearest neighbouring star is not 4 light-years away. It is 12 or 15, the handful of bright stars that dominate Earth's sky. Sirius, Vega, Arcturus have no equivalents here. Instead, the brightest objects in your sky might be 3rd or 4th magnitude, faintly visible but unremarkable. The constellations, if your civilization bothered to draw them, would be sparse and widely spaced. Looking at your sky, you would not feel the intuition of cosmic crowding that Earth's sky generates. You would feel something closer to cosmic scarcity. The universe, from your vantage point, would look like a place where stars are uncommon things, scattered thinly across an expanse of dark that stretches unbroken for enormous distances in every direction. If your civilization developed astronomy, the concept of interstellar travel would seem even more absurd than it does from Earth. Your nearest target would be twice as far. The void surrounding you would be deeper, darker, and more featureless. The sense of isolation would be embedded in your sky from the first night your species ever looked up. Now move yourself somewhere far more extreme. Place yourself on a planet orbiting a halo star, one of the ancient, metal-poor objects orbiting the galaxy, on a long, looping trajectory tens of thousands of light-years above the galactic plane. You step outside at night, and what you see is almost nothing. The sky is black, not the rich, star-flecked black of a clear night on Earth. A true, deep, empty black, interrupted by only a small scattering of visible stars, perhaps a few dozen bright enough for your eyes to detect. Your nearest stellar neighbour may be 30, 50, or 100 light-years away. If you turned every propulsion concept humanity has ever imagined toward that neighbour, even the most ambitious would require centuries or millennia to reach it. Below you, far in the distance, the disk of the Milky Way stretches across part of the sky like a faint, flat ribbon of diffuse light. It is beautiful in its way, a pale band of accumulated glow from billions of stars too far away to resolve individually, but it is clearly distant. Clearly elsewhere. You are not part of that dense ribbon of stellar activity. You are above it, looking down at it from a position so remote that the entire bustling disk of the galaxy feels like something happening to someone else. From your halo world, the universe would feel profoundly, almost oppressively empty. The night sky would teach your civilization, from its very first generation, that existence is a solitary condition, that stars are rare, that the void is the natural state of things, and everything else is an anomaly. Now go to the opposite extreme. Place yourself on a hypothetical planet deep in the galactic core, in that furnace of stellar density we already described. You step outside, and the sky assaults you. Thousands of stars blaze in every direction, many of them brighter than Sirius appears from Earth. Some are close enough that their disks might be faintly resolvable to sharp eyes, not points but tiny circles of light. The combined glow of the stellar background creates a sky that never truly darkens. Night on your world is a kind of permanent twilight, lit by the accumulated radiance of millions of neighbouring suns. The nearest stars are close enough that their gravitational effects on each other are significant, close enough that passing stars periodically disturb planetary orbits. Stars in the core pass near each other frequently enough to disrupt planetary orbits. Your world, if it existed at all, would be battered by gravitational perturbations from passing stars, bathed in intense radiation from nearby supernovae, and subjected to the tidal influence of the supermassive black hole itself. The sky would be glorious. It would also be violent. The core is the one place in the galaxy where the distance between stars shrinks to something approaching intimacy, and that intimacy comes at the cost of stability. Planets in the core may not survive long enough for complex life to develop. The closeness that makes the core sky brilliant also makes it dangerous. These three vantage points, the interarm desert, the halo exile, and the core inferno, bracket the range of stellar experience within a single galaxy. And notice what they reveal. The only region where stars are genuinely close together, the core, is likely too hostile for the kind of stable, long-duration conditions that complex life seems to require. The regions where conditions are calm enough for life to develop, the disk and the halo, are precisely the regions where stars are separated by distances that make contact between them functionally impossible. The galaxy appears to have arranged itself so that proximity and habitability are inversely correlated. The places where stars can see each other up close are the places where they are most likely to destroy each other. The places where stars can nurture planets in peace are the places where they are most utterly alone. This pattern is not a coincidence. It is a consequence of gravity and stellar dynamics. Dense environments produce frequent gravitational interactions that scatter planets and bathe them in radiation. Sparse environments produce the stability needed for planetary systems to persist for billions of years, but at the cost of isolation so extreme that the nearest neighbour is unreachable. The galaxy does not offer a middle ground. There is no region where stars are both close enough to visit and calm enough to live near. The architecture of stellar distance is not merely inconvenient. It is structurally opposed to the combination of habitability and connectivity that interstellar contact would require. But the centre comprises a tiny fraction of the galaxy's total volume. The vast majority of the Milky Way's real estate lies far from the core, in the disk, in the interarm regions, in the halo, and in all of those regions, the defining characteristic is not stellar density, but stellar absence. The galaxy has a dense heart and an almost empty body. The centre is the exception, the emptiness is the rule. Now let me show you what this means for communication. Earlier, I described the 4-year signal delay between Earth and Proxima Centauri. 4 years out, 4 years back. 8.5 years for a single exchange. That was the nearest star, the shortest possible delay. Scale that up across the galaxy, and communication becomes not merely slow but structurally impossible in any form that resembles human conversation. Consider a star 20 light-years away, not a distant star by any reasonable standard. 20 light-years places you well within the Sun's local stellar neighbourhood, a region containing maybe 100 known stars. A signal sent to a planet orbiting a star 20 light-years away would take 20 years to arrive and 20 years to return. A single question and answer exchange would span 40 years. A child born on the day the message was sent would be entering middle age before the reply reached Earth. 2 exchanges would consume 80 years. No living human could participate in a 3-exchange conversation. Now move to 100 light-years. Still firmly within the Milky Way's local arm, a signal would take a century each way. 200 years for 1 exchange. No civilization in human history has maintained continuous institutional attention on a single project for 200 years. Empires rise and fall on shorter timescales. Languages evolve, governments dissolve. The entity that sent the message might not exist in recognizable form by the time the answer comes back. At 1,000 light-years, communication becomes something that only a species thinking in geological time could attempt. 2 millennia for one exchange. The signal would travel as long as the span separating the Roman Empire from the present day. Whoever receives the reply would need an unbroken chain of cultural memory, stretching across dozens of generations, just to remember that a message was sent. At galactic scales, communication becomes outright fantasy. A signal from one side of the Milky Way to the other would take 100,000 years to cross the disk, 200,000 years round trip. That duration exceeds the entire history of human civilization many times over, and spans 2/3 of the total existence of our species. The species that sent such a message might have evolved into something unrecognizable, gone extinct, or transcended biological existence entirely before the reply arrived. And these are light speed signals, the fastest possible communication. Nothing carries information faster than light. There is no cheat code, no shortcut, no wormhole technology sitting in a laboratory waiting to be deployed. The speed of light is not an engineering constraint to be overcome. It is a law of physics written into the structure of space-time. Information cannot travel faster than 300,000 kilometers per second. Full stop. This means the Milky Way cannot function as a connected system, not in any meaningful sense. There is no possibility of a galactic civilization coordinating activity across the disk. No possibility of real-time governance, trade, diplomacy, or cultural exchange between stars separated by more than a handful of light-years. Even at the tightest stellar spacings, communication delays measured in years make anything resembling human interaction impossible. At typical galactic distances, the delays stretch into millennia and beyond. The galaxy, on the timescale of communication, breaks apart into billions of isolated zones. Each star system exists in its own temporal bubble. Events happening at one star are unknown at every other star for years, decades, centuries, or millennia, depending on distance. The Milky Way is not a single entity experiencing time together. It is a vast collection of individual points, each experiencing its own version of the present, all of them separated from each other by information delays so severe that the concept of simultaneity becomes meaningless. Think about what this implies for the night sky. Every star you see is not showing you the present, it is showing you the past. Sirius is showing you what it looked like 8.6 years ago. Betelgeuse is showing you roughly 700 years ago. Deneb is showing you 2,500 years ago. The stars in the Milky Way band are showing you a patchwork of moments stretching from decades to millennia into the past, all projected onto the same apparent plane by your depthless vision. The sky is a mosaic of different times. No two stars are showing you the same moment. The galaxy you observe tonight does not exist as a unified present-tense object. It exists as a collection of temporal fragments, each one delivered to your eyes after a journey through empty space, lasting years or centuries or longer. This temporal fragmentation is not a quirk. It is a fundamental consequence of the distances between stars, and it means that the galaxy you see is not the galaxy that is. By the time light from a star 1,000 light-years away reaches your eye, 1,000 years of events have occurred at that star that you cannot know about. Stars have been born and died. Planets have formed. Civilizations, if they exist, have risen and perhaps fallen. None of that information has reached you yet. It is still traveling through the void, photon by photon, light-year by light-year, crawling toward you at the fastest speed the universe allows, and still not getting here for centuries. The galaxy, in this light, is less like a city and more like an archipelago, a chain of islands scattered across an ocean so wide that travel between them takes lifetimes, and communication takes generations. Each island can see the lights of distant neighbours twinkling on the horizon, but the distances are so great that visiting those neighbours is effectively impossible. Sending a message and receiving a reply takes longer than any single inhabitant will live. The islands know that others exist. They can see them. They can study their light, but they cannot touch them, cannot speak to them in any meaningful way, and cannot coordinate with them on any timescale that matters for living beings. This is the galaxy you are looking at when you step outside on a clear night and feel awe at the richness of the sky. You are looking at an archipelago of isolation. Every star is an island. Every gap between them is an ocean that not even light can cross quickly. And the most striking feature of this archipelago is not the islands themselves, but the water between them, the void, the silence, the incomprehensible stretches of empty space that separate every point of light from every other point of light by distances that make meaningful contact a near impossibility. The Milky Way contains 400 billion stars. That is a fact. But it also contains roughly 8 trillion cubic light-years of space, and the overwhelming majority of that space is vacuum. Stars are rare, light is rare, matter is rare. The galaxy is not a bright, dense, teeming structure. It is a dim, sparse, mostly empty one, a place where the distance between things is the defining feature, where the void is the main character, and the stars are supporting actors, outnumbered and outvolumed by the nothingness surrounding them, by factors so extreme that the word empty barely begins to capture it. And the galaxy is just one galaxy. The Milky Way is one spiral among 2 trillion galaxies in the observable universe. Between those galaxies lie intergalactic voids that make interstellar distances look intimate. Millions of light-years of space between galactic neighbours, each light-year containing that same sparse scattering of hydrogen atoms, that same cold darkness, that same featureless silence. If interstellar space is an ocean, intergalactic space is the gap between continents. But this is a story about the distance between stars, not the distance between galaxies. And the distance between stars is already bad enough to reshape how you should think about the night sky forever. Here is what the galaxy really looks like, stripped of every visual illusion. It is a disk of mostly nothing. Sprinkled through that nothing, at separations measured in light years, are tiny thermonuclear furnaces, each one surrounded by a thin shell of gravitational influence where planets might orbit and chemistry might occur. Beyond those thin shells lies the void again, stretching light years in every direction until the next tiny furnace appears. And that furnace is surrounded by its own thin shell, and then more void, and then another furnace, repeating 400 billion times across a structure 100,000 light-years wide. The furnaces are magnificent. Each one is a roaring engine of fusion, converting millions of tons of hydrogen into helium and energy every second. Some are small red embers barely visible across a few light-years. Others are blue-white giants that would dwarf our sun 1,000-fold. They come in every size, every temperature, every age. Some are newborns still swaddled in the gas clouds that birthed them. Others are ancient objects older than the Earth, slowly cooling toward eventual death. Each one is a universe of physics and chemistry unto itself, but between them is nothing. And the nothing is so much vaster than the something that the something almost disappears. The galaxy does not look full when you see it accurately. It looks like a structure where fullness was attempted and mostly failed, where matter gathered into intense but tiny concentrations separated by absences so dominant that crossing from one concentration to the next defeats every technology and every communication method that physics permits. The night sky lies to you. It tells you the stars are close. It tells you the galaxy is rich. It tells you the cosmos is crowded with light and warmth and potential connection. The truth is that every star you see is stranded. Every point of light is an island, so remote from every other island that the ocean between them defines the galaxy more than the islands ever could. You are looking at isolation, billions of instances of it, projected onto a flat sky that strips away the depth and hides the void. And it is into that void, and what it means for everything we thought we understood about connection and belonging in the cosmos, that we must now make our final descent. There is a question that has haunted science for over 75 years. It was first posed informally over lunch at Los Alamos National Laboratory in 1950 by physicist Enrico Fermi. The story goes that Fermi and his colleagues were discussing the probability of extraterrestrial civilizations when Fermi looked up from his meal and asked a question so simple it silenced the table. Where is everybody? The question has since become one of the most famous unsolved problems in science. The Fermi paradox, as it is now called, rests on a seemingly airtight chain of logic. The Milky Way is billions of years old. It contains hundreds of billions of stars. Many of those stars have planets. Some fraction of those planets likely developed conditions suitable for life. Given enough time, some fraction of living worlds should have produced intelligent civilizations. Some fraction of those civilizations should have developed technology capable of sending signals across interstellar space, or even of spreading physically from star to star. Even if that spreading happened slowly, at a small fraction of the speed of light, the galaxy is old enough that a single expansionist civilization could have colonized the entire disk many times over. The galaxy should be buzzing with signals, teeming with probes, marked by the unmistakable fingerprints of technological activity. It is not. The sky is silent. No confirmed signal from an alien intelligence has ever been received. No probe of extraterrestrial origin has ever been detected. No structure, no beacon, no artifact, no emission that unambiguously indicates the presence of another technological civilization has been found anywhere in the observable cosmos. The silence is total. Dozens of solutions to the Fermi paradox have been proposed over the decades. Perhaps life is far rarer than optimistic estimates suggest. Perhaps intelligent life destroys itself before it can spread. Perhaps civilizations choose to remain hidden. Perhaps they exist but communicate in ways we cannot detect. Perhaps the galaxy is colonized and we simply have not noticed. Each proposed solution carries its own assumptions, its own implications, and its own uncomfortable consequences. But there is one explanation that almost never gets the weight it deserves, and it is the simplest. The distances between stars are so enormous that crossing them, even for a civilization millions of years more advanced than ours, may be so difficult, so slow, and so resource-intensive that interstellar expansion simply does not happen at the rates the paradox assumes. The silence is not mysterious. It is not a puzzle requiring exotic solutions. It is the predictable, expected outcome of a galaxy where the space between stars is the dominant structural feature and where that space resists being crossed by anything, including civilizations far beyond our own. Think about what we have established across this story so far. The nearest star is 4.24 light-years away. At the fastest speed any human spacecraft has ever achieved, reaching it would take over 70,000 years. Even at 20% of the speed of light, the most ambitious propulsion concept ever seriously funded, the trip would take over 20 years with no ability to stop, orbit, or land. Communication with the nearest star requires at minimum an 8.5-year round trip at light speed. The average gap between stars in our part of the galaxy is roughly 5 light-years, with many stars separated by far more, and these gaps are filled with almost nothing. Cold vacuum, stray hydrogen atoms, darkness extending trillions of miles in every direction. Now ask yourself what interstellar colonization actually requires. Not in science fiction, not in optimistic projections. In physical reality, it requires transporting enough material, energy, and biological or technological complexity across those gaps to establish a self-sustaining presence at the destination. It requires either keeping living organisms alive for decades or centuries during transit, or sending machines sophisticated enough to build infrastructure upon arrival. It requires solving propulsion, shielding against cosmic radiation and interstellar dust impacts at high velocities, maintaining systems over journeys lasting longer than most civilizations endure, and doing all of this across a void that offers no resources, no shelter, and no possibility of rescue if anything goes wrong. Even a civilization a million years ahead of us in technological development faces the same physics we do. The speed of light does not bend for advanced species. The vacuum between stars does not become less empty because someone clever is trying to cross it. The energy requirements for accelerating meaningful mass to significant fractions of light speed do not decrease with technological progress. They are set by the laws of physics, and those laws are not negotiable. This does not mean interstellar travel is impossible. It means it is hard in a way that no terrestrial challenge has ever been hard. Crossing an ocean on Earth is difficult but achievable because the ocean provides buoyancy, contains resources, and the crossing takes weeks or months, not millennia. Crossing the gap between stars provides nothing. No buoyancy, no resources, no shelter, no way to resupply. And the crossing takes years at best, centuries or millennia at worst. The interstellar void is not an ocean. It is a wall of time and emptiness so thick that pushing through it requires commitments of energy and patience that may exceed what any civilization is willing or able to sustain. The Fermi paradox assumes that interstellar colonization, once possible, proceeds inevitably, that a civilization capable of crossing the gap to one star will then cross it again and again and again, spreading exponentially across the galaxy. But what if the gap is so punishing that most civilizations cross it once, or a few times, and then stop? What if the energy cost, the time investment, the risk, and the diminishing returns of colonizing yet another star system, separated by decades of travel from the last one, make expansion plateau long before it reaches galactic scale? What if the galaxy is not silent because civilizations destroy themselves or hide, but because the architecture of stellar distance naturally limits how far any civilization can spread? A 5 light-year gap between stars does not sound like much in the abstract, but we have seen what that gap actually contains. 30 trillion miles of emptiness, decades of travel at speeds we cannot yet achieve, years of signal delay for even the simplest message. A civilization that colonizes its nearest neighbor has accomplished something magnificent, but it then faces the same gap again to reach the next star, and the next, and the next. Each crossing requires the same enormous investment. Each colony is separated from its parent by communication delays measured in years. Coordination between colonies is impossible on human timescales. Each outpost becomes, within a generation, an effectively independent entity, separated from every other entity by the same savage distances that defined the original crossing. The galaxy does not connect. It fragments. Distance does not create a network. It creates a scattering. Each star system, whether inhabited or not, exists in its own temporal and spatial bubble, linked to its neighbors only by the thin thread of light-speed signals that take years or decades to arrive. A galactic civilization in any meaningful sense, a unified entity with shared governance, shared culture, shared purpose, is physically impossible. The speed of light forbids it. The distances between stars enforce it. What you might get instead is a collection of isolated settlements, each one separated from every other by chasms of time and space, each one evolving independently, drifting culturally and perhaps biologically, becoming as foreign to one another as civilizations on different continents became foreign before the age of radio. The silence of the cosmos, viewed through this lens, is not a paradox at all. It is a consequence. The galaxy is structured for isolation. The space between stars is not an incidental feature that civilizations root around. It is the defining feature of the stellar universe. It determines what travel can mean, what communication can achieve, what contact is possible, and what is forever out of reach. The answer to Fermi's question may not require invoking great filters, or cosmic predators, or civilizations choosing silence. It may simply be that the galaxy is too empty, too vast, and too structurally hostile to connectivity for the kind of teeming, signal-rich cosmos the paradox imagines. Where is everybody? Possibly right where they started, on their home worlds. separated from us by voids too wide to cross often enough and too deep to shout across loudly enough for the message to arrive with any strength. Not dead, not hiding, just far away. In a galaxy where far away is the default condition of everything. But there is another dimension to the silence that most people never consider. Even if civilizations exist at distant stars, even if they are actively broadcasting signals into space, even if they want to be found, the distance between stars does not merely delay those signals, it destroys them. Every electromagnetic signal, whether it is a radio wave, a laser pulse, or any other form of light, obeys the inverse square law. This law states that the intensity of a signal decreases with the square of the distance from the source. Double the distance, and the signal strength drops to 1/4. Triple the distance, and it drops to 1/9. At 10 times the distance, only 1/100th of the original intensity remains. At 1,000 times the distance, 1/1,000,000th. The inverse square law is not a limitation of engineering. It is a geometric consequence of how energy spreads through three-dimensional space. A signal emitted from a point source radiates outward in a sphere. Herika, the surface area of that sphere grows with the square of its radius. The same total energy must spread across that growing surface. At interstellar distances, the sphere becomes so enormous that the energy per unit area at the receiving end drops to almost nothing. Consider what this means for a real signal. Imagine a civilization orbiting a star 100 light-years from Earth. They build a radio transmitter of extraordinary power. They aim it directly at our solar system with perfect precision. They broadcast at 100 megawatts, roughly the output of a large commercial radio station multiplied by 1,000. That signal travels 100 light-years, expanding as it goes, the energy spreading across an ever-growing sphere. By the time it reaches Earth, the signal has spread across a sphere with a surface area exceeding 10 to the 37th square meters. The power per square meter arriving at Earth drops below 10 to the negative 29th watts. That is a decimal point, followed by 28 zeros and then a 3. To put that in context, the background noise at radio frequencies generated by the cosmic microwave background, by the Milky Way's own synchrotron radiation, by the Sun, by Jupiter, by Earth's own atmosphere, by human-made radio interference, all of that noise produces signals many orders of magnitude stronger than the arriving transmission. The alien broadcast, sent with 1,000 times the power of any radio station on Earth, aimed precisely at us, is buried so far beneath the noise floor that detecting it would require either an antenna of extraordinary size, an integration time spanning years, or both. And this is for a source only 100 light-years away. A star at 1,000 light-years produces a signal 100 times weaker still. At 10,000 light-years, it is 10,000 times weaker. At galactic distances, the signal from even a civilization-scale transmitter disappears into the cosmic background like a whisper in a hurricane. The SETI program has been searching for extraterrestrial signals since 1960. In over 6 decades of observation using progressively more sensitive instruments, no confirmed artificial signal of extraterrestrial origin has been detected. This is often presented as mysterious, as evidence of cosmic loneliness or as a data point in the Fermi paradox. But the inverse square law suggests a simpler explanation. We may not have detected signals, because the signals, if they exist, are too weak to detect at the distances involved. The most sensitive radio telescope currently operating for SETI purposes can detect signals of roughly 10 to the negative 26 watts per square meter under ideal conditions. This means it could theoretically detect a powerful, tightly focused transmission from a distance of perhaps a few hundred light-years under ideal conditions, but only if the beam happened to be aimed precisely at Earth, and only if our instruments were tuned to exactly the right frequency at the right moment. An omnidirectional broadcast, the kind a civilization might produce simply through its normal radio and television emissions leaking into space, becomes undetectable at a distance of just a few light-years with current technology. Our own television broadcasts, which have been radiating into space for roughly 90 years, are already undetectable beyond a few light years. They have not vanished. They are still travelling outward, but they have spread across such an enormous sphere that the energy per unit area is indistinguishable from noise. This means that the volume of space we have meaningfully searched for extraterrestrial signals is tiny. Not small, tiny. A sphere of 15 light-years radius contains roughly 60 known star systems. The Milky Way contains 400 billion. We have effectively searched barely 2/1000ths of the galaxy's volume. The silence we have observed is not a galaxy-wide silence. It is the silence of our immediate doorstep. A doorstep so small relative to the galaxy that finding it empty tells us almost nothing about whether the rest of the house is occupied. Even dramatically increasing our detection capability does not solve the fundamental problem. Building a radio telescope 10 times more sensitive extends the detection range by a factor of roughly 3, because the inverse square law means sensitivity scales with the square root of distance. A telescope 100 times more sensitive extends the range by a factor of 10. To survey the entire galaxy for signals equivalent to our own leakage radiation, we would need instruments billions of times more sensitive than anything currently operating, or we would need transmitters at the source billions of times more powerful than anything we have built. The distance between stars does not just prevent travel, it does not just delay communication, it attenuates signals so severely that civilizations actively trying to announce their presence might be invisible to each other across the typical gaps that separate stellar neighbors. A galaxy could contain thousands of broadcasting civilizations, each one shouting into the void with all the power it can muster, and the inverse square law would reduce their shouts to silence long before those signals reach the nearest listener. The void between stars is not just empty, it is absorptive. It soaks up signals, it dilutes energy. It takes the most powerful transmissions a civilization can produce and spreads them across such inconceivable volumes that they arrive at their destination as thermal noise, indistinguishable from the random crackle of the cosmos. This is perhaps the most sobering implication of interstellar distance. The galaxy might not be silent at all. It might be roaring with signals from civilizations scattered across its disk, but the roar, diluted by the inverse square law across light years of expanding spherical wavefronts, arrives at every potential listener as a whisper too faint to hear. The problem is not that nobody is talking. The problem is that the distances between speakers are so vast that talking and being heard are no longer the same thing. Now go back outside, one more time. Look up at the sky you looked at when this story began. It has changed. Not physically. The photons striking your retina are the same photons that were always going to arrive at this moment, emitted years or centuries or millennia ago by stars that may or may not still exist in the form you see them. The sky has not moved. The stars have not rearranged. The Milky Way still cuts its bright band across the darkness. Everything looks exactly the same. But you are different. And because you are different, the sky means something different now. Before, those thousands of visible stars felt like neighbors, like a community, like evidence of a galaxy teeming with presence. You looked up and felt, perhaps without articulating it, that the universe was full, that those points of light represented a kind of cosmic companionship, that somewhere out there, among all those stars, someone else might be looking back. The sky felt populated, connected, alive with possibility. Now you know what those points of light actually represent. Each one is a thermonuclear furnace burning in absolute solitude, separated from every other furnace by trillions of miles of cold, dark, featureless emptiness. The apparent proximity is a lie told by your eyes, which cannot measure depth at astronomical distances, and so flatten everything onto a single plane where closeness is an illusion. The density is a lie told by perspective, which stacks thousands of light years of sparse depth into a single visual corridor until the accumulated glow of distant, isolated stars mimics the appearance of crowding. Every intuition the sky generates about closeness, about neighborliness, about a universe where things are near each other, is wrong. The stars are not close. They are not neighbors. They are not connected to each other in any physical sense that matters for travel, communication, or contact. Each one exists in its own vast territory of empty space, a territory so large that crossing from one to the next would take our fastest spacecraft tens of thousands of years. Even light, the fastest thing in the universe, needs years to bridge the shortest gaps and millennia to cross the galaxy. No signal, no ship, no message, no force in nature can make the stars feel truly close to one another. The distances forbid it, the physics enforces it, the emptiness is absolute. And this is not a special condition affecting a few unlucky stars in sparse regions of the galaxy. This is the universal condition of stellar existence. Every star in the Milky Way, all 400 billion of them, lives in this isolation. Every star is surrounded by light years of void. Every star is separated from its nearest companion by a gap so severe that even the most optimistic propulsion concepts require years or decades to cross it. The galaxy contains 400 billion points of light and 17 trillion cubic light-years of darkness, and the darkness dominates so completely that the points of light are statistical anomalies in an otherwise empty structure. The night sky is a map of loneliness drawn in light. Consider what this means for meaning itself. Humans evolved on a planet where everything is close to something. Trees grow next to other trees. Animals live in herds and flocks and schools. People build cities where thousands of individuals share a few square miles. Our entire evolutionary history trained us to expect proximity, to expect neighbors, to expect that where there is one, there are many, and that the many are reachable. Our deepest social instincts, our emotional architecture, our very sense of belonging, all of it was built in an environment where closeness was the default state of living things. The stellar universe violates every one of those instincts. It is a place where closeness is the rarest condition, and separation is the norm. A place where the nearest neighbor is years of light-speed travel away, and the average neighbor is beyond the reach of any technology humanity has ever imagined. A place where the sky looks crowded but the reality is empty. Where 400 billion stars sounds like abundance but distributes across the galaxy as scarcity. Where even the most packed regions of the galactic disk are mostly vacuum, and even the nearest stellar systems are functionally unreachable. This violation goes deeper than inconvenience. It challenges something fundamental about how humans relate to the cosmos. We want the universe to be a place where contact is possible, where the light years can be crossed with enough ingenuity, where the stars in the sky represent potential destinations rather than permanent exile. Every science fiction story about interstellar travel, every film showing spacecraft jumping between star systems, every narrative about galactic civilizations meeting and communicating across the void, all of them are acts of emotional rebellion against the architecture of real space. They are stories we tell ourselves because the truth is too isolating to accept without protest. The truth is that a sky full of stars describes a universe where almost nothing is close to anything else, that the galaxy's apparent richness is, on human terms, a landscape of near-total separation, that the very thing which makes the night sky beautiful, the abundance of visible stars, is also the thing that makes the cosmos most cruel, because every one of those stars is beyond meaningful reach. The beauty and the cruelty are the same phenomenon viewed from different angles. You see thousands of stars and feel wonder. You learn what the distances between them actually mean, and the wonder does not disappear, but it acquires a weight, a sadness, a recognition that looking and reaching are separated by a gulf so wide that one does not imply the other. The galaxy is not what it looks like. It looks like a glittering treasure chest of destinations. It is actually a cathedral of emptiness with candles burning at intervals so wide that walking from one to the next would consume lifetimes. The candles are beautiful. They are real. They illuminate their tiny corners of the darkness with fusion light that has burned for billions of years, but the darkness between them is the cathedral's true substance. The darkness is the architecture, the candles are decoration. We live on a planet orbiting one of those candles. Our candle is ordinary, a middle-aged yellow dwarf burning hydrogen in a suburb of a spiral arm 26,000 light-years from the galactic center. From our position, we can see a few thousand other candles with our naked eyes and billions more with our telescopes. We know their temperatures, their compositions, their distances, their motions. We have catalogued them, named them, studied their light with instruments of extraordinary sensitivity. We know more about the stars than any generation of humans before us. And yet we cannot touch a single one. We cannot visit the nearest candle. We cannot send a message and expect a reply within a human lifetime except to the very closest neighbours, and even those replies would span years. We are stranded at our candle, surrounded by the glow of billions of others, able to see them all and reach none of them. The universe shows us everything and gives us nothing. The stars are a gallery of wonders visible through unbreakable glass. This is the terrifying truth about the distance between stars. It is not merely that the distances are large. Large is a word for mountains and oceans and continents. In fact, the distances between stars are not large. They are annihilating. They do not merely make travel difficult. They make travel on any timescale compatible with human existence effectively impossible for all but the very nearest targets. They do not merely slow communication. They stretch communication to the point where conversation becomes a multi-generational relay spanning decades or centuries. They do not merely separate civilizations. They isolate them so thoroughly that each star system becomes, for all practical purposes, its own universe, cut off from every other universe by a moat of empty space-time that nothing can cross quickly. The sky full of stars is the cruelest illusion in nature. It promises a cosmos of connection and delivers a cosmos of exile. It paints a picture of closeness on a canvas of incomprehensible distance. Every point of light whispers that you are part of something vast and connected and full. The physics whispers back that you are alone, that your candle burns in isolation, that the other candles are beautiful and real and permanently, structurally, almost inconceivably far away. 400 billion stars, 8 trillion cubic light-years of space, and between every pair of stars a silence measured in years. That is the Milky Way, not a crowded metropolis of suns. A scattering of embers in an ocean of dark, each one burning fiercely and each one burning alone, separated from every other by a void so dominant that it defines the galaxy more completely than the stars themselves ever could. You will go outside again someday and look up. The stars will still be there, thousands of them, beautiful and bright and seemingly close. And now you will know what you are actually seeing. Not a sky full of neighbours, a sky full of castaways, each one stranded on its own tiny raft of fusion light, drifting through an emptiness so vast that the distance between any two of them is worse than you ever imagined, worse than your eyes will ever show you, worse than your brain was ever built to understand. The distance between stars is not a number, it is a verdict. And the verdict is this: the galaxy is full of light, but the light is alone.